So today we continue studying some sort of mathematics for machine learning. And today's topic is, let's say, probability theory, Bayes theorem. And we will talk a little bit about the Bayes classifier. And I will tell you why it's called naive Bayes classifier and why do we need all that Bayes theorem at all. First of all, I want to tell you a little bit about let's say, classification of models that, let's say, discriminative versus generative methods of classification. So we have basically two types of models when we are talking about some sort of classification. That may be a simple discriminative model. That means that when you are putting some data into the model, you get as a result just some sort of classification. So you are just getting some class of that data point that you have put into your model. That seems quite simple. And you may, of course, ask, well, what does the generative model do if we are performing the same problem of classification? Well, generative model is a little bit, let's say, more complicated model because it assumes some sort of probability distribution that is generating your data points. So when you are creating a generative model, you are assuming that your data points come from some random process, and that random process behind it, there is some sort of distribution function, and you are trying to recover that distribution function with your generative model. Why do you may want to do that? You don't need that basically for, let's say, classification, because you can have classification models that do not reconstruct that sort of function for you. But you may need that function if you want to generate some more points that look like your data points from your data set. So you can equip your data set with some additional points that your model will generate for you. And probably you have heard about, let's say, some sort of neural networks like GAN, so generative adversarial networks. And even on the first lecture, I have probably shown you a picture of a cat with the style of, let's say, Kandinsky pictures. So some sort of Kandinsky cat. So you probably know about style transferring right now, and you may guess that if I have a lot of data points that are basically pictures of Kandinsky, my generative model can somehow recover that distribution function behind that pictures and try to generate some more Kandinsky-like pictures, and so on. So we can add some more points. So if we compare these two models, we can say these two types of models, we can say that discriminative methods are in general are more simple because you are not required to get any idea about the probability distribution behind them. And you probably might guess that I cannot just search for any probability distribution. That's impossible because we have too many functions in the world. So we always restrict ourselves to some sort of family of functions. So for example, you may say, I'm searching for some sort of normal distribution. I'm searching for some other distribution. If you are using neural networks, you can use a very, very complicated function with many, many parameters. So for a normal distribution, you have, well, how many parameters? Yes, you have just two parameters. If you are trying to model some function with a neural network, you may have 1 million parameters, 1 billion parameters, so many, many parameters. That's okay. So discriminative models are in general more simple. They are quite effective in producing results on large data sets. And of course, they have sort of minus. They do not provide you any insight in the interpretation of the data. or provide you less insights into that interpretation. On the other hand, generative methods, you need to first establish some sort of probabilistic model to create your generative classifier, but they allow you to use some sort of problem-specific knowledge when you are building the model, and they may help you to interpret the data you have. So that's really good. They can, of course, provide you with some sort of uncertainty estimate. That's good as well. So depending on your problem, you may want to have either just a simple discriminative model if you just want to get some class of your data point and that's all. Or you may want to have a generative model if you want some sort of estimate of that probabilistic distribution behind your data points, and that will maybe give you some sort of more insights into your problem. Okay, so why am I telling you all that about? Because right now we will get a little bit through some mathematics, but then we will get to naive Bayes classifier, and that will be a generative model. So we will be estimating some sort of probability distributions that are behind that data point that I'm passing to my Bayes classifier. Okay, but a little bit about probability, some concepts that we will need. So some concepts that we need are, first of all, the idea of the elementary outcome, the idea of probability and probability distribution. So what is that, and so on. So the atoms of every probability theory problem are elementary outcomes. And the key concept of an event is a complex outcome that can basically include or some sort of incorporate multiple elementary outcomes. So how it looks like in practice. So you have a problem and you are thinking what kind of outcomes may happen in your probabilistic problem. And you want to get first some sort of elementary events or elementary outcomes. You want to have some sort of collection of that. And this collection, what you want from that collection is that all events or all outcomes in that collection to be first mutually exclusive. So if you are saying that some event happened, then some elementary event happened, because events may be non-elementary, then things will be a little bit different. But we start with atoms, let's say, with elementary events. And we say that we want them to be mutually exclusive. So one happened, then none of the else events has happened. We want them to be collectively exhaustive. So that means that whatever happens in your experiment, in your trial, you want to have some elementary event or events that are describing this situation. And the second thing, and the third thing that we want to have is, let's say, the right granularity. So you may have some elementary events, but they don't have some sort of right granularity. They either don't capture all the specifics of your experiment that you are doing, or they are too granular and they encapsulate some information that you want to get rid of. So you don't want that in your experiment. To get a little bit more idea about that, let's consider this sort of trying to create some, let's say, space of elementary outcomes or elementary events when I am performing experiment with rolling a dice. So I have a dice with 6 faces, and I'm trying to roll that. And I want to describe that in some sort of probabilistic manner. And the first thing I start is creating a list of elementary outcomes that I want to have. Let's go through some of the possible ideas that I may have, and let's a little bit criticize them, which one is good, which one is not very good. So if I am taking a set, let's say, of events that I'm seeing on the upper face of a dice after I rolled it, numbers 1, 2, 5, or 6. Is this a good choice for the space of elementary outcomes?
No,
No,
because there is
we don't
one.
have 3 and 4.
Yes, absolutely correct. So it's not exhaustive. So it's not exhaustive. We are missing some outcomes that I may have in my experiment. If I am taking numbers 1, 2, 3, 4, 5, 6. Well,
It's good.
yeah, seems good. So for most purposes, we will have that will suffice for most purposes. Okay, the result is divisible by 2, divisible by 3, or divisible by 2 or 3.
Maybe for some case, but not for most of it.
What about number 6?
Yes, that's correct. So number 6 will fall into, let's say, few categories. So I have numbers divisible by 2. I have numbers divisible by 3, numbers that are not divisible by 2 or 3. But I have 6 that falls into category divisible by 2 and divisible by 3. So they are not mutually exclusive. So that's why it cannot be an elementary outcome, because at least in one case, you have two outcomes together. They are not exclusive. That's too bad. Or I may have a set, let's say I have 1 on the dice and it rains. I have 1 on the dice and there's no rain. I have 2 on the dice and it rains, and so on and so forth. Is it good?
If we are talking about just rolling the dice, that's too much little events to be considering.
Well, too many events, let's say, yeah?
Yeah,
so it's too many events. Yeah, you're right. When we are talking about, let's say, mutually exhaustive or exhaustive or mutually exclusive, it's everything okay. So that really describes our experiment. But when we are getting to practice, we may feel that these events are, let's say, too granular. So I have included some information into that elementary outcomes that we probably don't need. Well, maybe you are exploring some sort of, I don't know, interconnection between rolling the dice and the weather behind the window. So probably in that case, you may want to have that. But if we are not considering some sort of fancy connections, then maybe you don't want to include the weather into the list of the events. So
probably it will be better to divide those sets on 2 sets and just use combination.
Well, we are interested in elementary events, so we need some sort of points in our stats. Yeah. About dividing or subdividing, that comes a little bit more about events. So don't mess elementary outcomes or elementary events with just events. So just event is some subset that may include some number of elementary outcomes. Yes, when we are rolling the dice, I can talk about the event of having a number divisible by 2 or divisible by 3, and I'm aggregating elementary outcomes. Now events, they can intersect. That's okay. They can intersect, so it will be pretty okay if we are talking about events that happen at the same time or something else. When we are talking about events, you have probably heard the word so-called sigma algebra. It sounds maybe a little bit scary, but there's nothing too complicated in there. So I'm not getting into all that mathematical details. I just want you to give some intuition behind it. So when we are talking about events that we are creating out of elementary outcomes, so we have a space of all elementary outcomes, and we are creating some events by aggregating these elementary outcomes. And what we want to be able to talk about, let's say, event A happened, or event A did not happen. So not A. So A or not A. So that means that if we are constructing all possible events that we are able to consider to, if we have in that list of events some event A, we want event not A to be in there as well. So that's why we say that that sigma algebra is closed under complementation. Yeah. So if I have there A, I should have not A in there. Of course, we want to be able about talking that events A and B happened. So if A and B are in sigma algebra, we want their intersection to be in that sigma algebra as well. If we are talking about A or B happened, we should have A union B in that sigma algebra. So that list of requirements, it's a really natural, let's say, list. So we are just asking that if I have that sigma algebra, it's listing me all the possible events I'm able to talk about. I want in that list to be some sort of combination of events. So if I'm seeing there's some event A and event B, I want to be their intersection, their union, their complements to be in that sigma algebra as well. Because it will be very strange if I'm able to say that A happened, but I cannot say that not A did not happen. Okay, if we have all that events, we want somehow to measure them. So how probable is event 1 or event 2 and so on and so forth. So we are like asking about measure on that sigma algebra. So right now, what did I started from and where I am now? So I started from some experiment. I considered that experiment and thought about all possible elementary outcomes that I may have. I said that they should be mutually exclusive, exhaustive list, so on and so forth. So now I have them. But that elementary outcomes, they are too granular. They are like sand that slips through your fingers. So you want something more. You want to talk about some sort of aggregated events. Okay, then we created a list of all possible aggregated events. So like with throwing the dice. So I don't care about the exact number. I just care about is it divisible by 2 or it is not divisible by 2? Is it divisible? Is it divisible by 3 or it's not divisible by 3? Then I said, well, I have these outcomes like divisibility, but of course it will be quite logical if I have event like divisibility by 2. I should have event like non-divisibility by 2. That would be strange if I'm able to talk about one thing, but I'm not able to talk about another thing. The same thing about divisibility by 3, and of course I want to be able about talking about that something is divisible by 2 and 3 at the same time, and so on. So we created a sigma algebra that captures that requirements. So I have a list of what can happen and what I'm interested in. Now I want to tell how probable is that something happens. So some event, not elementary, is happening. So I'm adding some sort of measure to that sigma algebra, and I'm assigning some numbers to my events that will tell me how probable is some event happening. So what is a measure? It's just some sort of function into extended real line. Why extended? I want to be able to assign, let's say, infinities at some point. So that will be just, let's say, convenient for me. And I call it measure if it satisfies the following properties. So it's non-negative. It's non-negative. It can measure empty set as a 0. very natural thing. So if you don't have any events, its probability should be 0. And that comes from the fact that our elementary outcomes were exhaustive. So our elementary outcomes are exhaustive. So you can never end up in a situation that something happened, but you are not capturing that. So all the time something should happen. So that means that the probability of happening nothing is 0, is definitely 0, because we defined it that way. And we want to have some sort of countable additivity. So if we are talking about some union of disjoint sets, in this case, we have disjoint events. So we have events, and we know that if A happens, then B does not happen. And if B happens, A does not happen. And we want to say that the probability of happening A or B is just a sum of that probabilities of happening A and happening B. Well, sounds quite reasonable. And if if set E has finite measure, the requirement that probability of empty set being 0 is met automatically, but that's that's more about math. So here is the formula, but that's okay. Okay, so about the probability, one more requirement that we want a measure of the whole set of our elementary outcomes to be equal to 1. Just some sort of normalization. So we all agree that probability 1 means that something definitely happens. And we want to say that all our elementary outcomes, they are exhaustive. So you never get out of the set. So the probability of happening some of them should be always 1. Okay, what else do I want you to tell? Before we get into that, one more thing I want you to tell about the random variables. I just want you to not mess up what is a random variable. So please never let's say never mix the outcome of something and a random variable. Because if we have some outcome of something, that's just some element of a set. While a random variable is a function that assigns you a real number to that element. So please don't mix that ideas, because in some cases it's really easy to do. So when we are throwing a dice, you might think that numbers 1, 2, 3, 4, 5, 6, that's some sort of your random variable. No, it's not. It's an elementary outcome. So let me draw you some small picture, and we really get quickly through that. So just in case you are confusing these two things, I want to unconfuse you a little bit. So here is my set, and here are some sort of elementary outcomes. So a random variable is a function that maps them onto the real line. So this is a random variable, let's say some x. And to feel that a little bit better, let's think about not throwing a dice, but tossing a coin. So if I have a coin, I have two sides of that coin, and I'm flipping it, and I get either one side, either another side. So I have some sort of avers and reverse, or how do you call them? So you have the 2 points. But if I assign numbers to them, so if I say, if I have the coin, I flip the coin, I have this result, and I map it to 0, and if I have some different result, I map it to 1, this mapping, this exact mapping, that will be your random variable. So that's really a bit easier to think in terms of a coin, because you don't have any numbers on its sides. So you can probably get it a little bit more intuitive if you are thinking about that sites like elementary outcomes and the function that maps them into some numbers. It can map to 0, 1, or I don't know, pi and e, or whatever you like, whatever you need, and that will be a random variable. Okay, conditional probability. We can talk about events that happen in case of, let's say, event A happens in case when we already know that event B happened. So in some sense, we are squeezing our space to the event B, and we are considering that subspace of event B, and we want to talk about event A in case of event B. We will need that for all our Bayesian classification thing and so on. So I guess we should spend a few minutes to talk about that. So the probability of A given B is called conditional probability. It's designated as, let's say, P from probability, and then I set the event that I'm interested in, that's event A. I draw a vertical line, and then comes the condition. So in case of B, so I know that B already happened, and I am talking about probability of A in case if B has happened. Here is an example of a joint event. So it's often designated as A intersection B. And you see here that this is the case when both A and B happened. There are a few interesting statements about this case. Let me check if I have it, or it's a bit later. Okay, maybe that comes a little bit later. So we will this situation, we are getting a bit closer to our main tools that we will use. First of all, we will use the idea of independence of the events. So maybe I will show you that a little bit later. So we will need the notion of the event's independence because we will talk about naive Bayes classifier, and we will suppose that some events are independent. So of course we need some sort of math that stays behind that. So we are saying that events are independent when the probability of the joint event of A intersection B is equal to the product of probability A and probability B. That may seem a bit not intuitive, let's put it that way. But I want to give you some sort of more intuition about this case. So let's let's gain some intuition. So right now I'm trying to make sense of a formula P A intersection B equals PA times PB. So at some point you might think, where does it even come from? The idea of this independence when I'm just talking about some sort of multiplication of probabilities. But I want to give you some, let's say, more intuitive definition of independent events. So from the word independent, you might, let's say, guess it in some sense. So suppose I have two events, A and B, and these events are such that when A happens, I don't get any additional information on B. If B happens, I don't get any additional information on A. So that means for them to be independent. So let me draw a picture for you. And let's think for a while. So here is my my space of the events. Here I am having event A. If you are thinking about some sort of probabilities, you can think about them like some sort of areas or something like that. Well, because it's measure, area, volume, that's all very closely related definitions. And here I have not A. So simple at this point. Now let me consider an event B. So here is my event B. Now can you tell me, are A and B dependent or independent?
Independent.
Independent.
You think that
yeah,
independent,
no,
and you think that dependent. Okay, so why?
Well, if A happens, we can guarantee that B doesn't happen.
Yes, absolutely correct. They are very, very dependent, because if A happens, I get a lot of information about B. I can definitely tell you that B did not happen. If B happens, I can definitely tell you that A did not happen. So I have an awful lot of information about events when one of them happens. So they are very dependent, very tightly dependent. Okay, so let's try to draw some independent events. So probably I will need to draw something like this. So in this case, I can really tell you that these events can be independent, because I have some part of B in A, I have some part of B in not A, and if these parts are well balanced, I can tell you that getting some information on A, like doing some experiment that tells me that A happened, I will not get any information on B. And of course, you can try to encapsulate that in the in formulae, and you can write, for example, so what is the probability of happening event A? Let's say the overall probability of happening event A. So I have some measure of probability of happening A, and of course I can divide it by measure of the whole set. It's equal to 1, but I guess you will understand in a moment why do I write it here. Now we suppose that B happened. So now I definitely know that event B happened. So now what's going on? So the whole space, after I have measured something, I performed some experiments, I know that B happened. So it means that my whole space is some sort squeezed into that B. So whatever I'm interested in, so some sort of, I want some new probabilities, some conditional probabilities of happening, of event A happening when I have B. That means that my whole space now have measure P of B, and event A happening in case of B, it's just this part. What is this part?
Intersection.
Yes.
A intersection B.
Yes, so that's P, A intersected B. And now looking at this formulae, you see that this is interesting part. So let me write it right here. So this is P of event A at condition B. This is just P of A. So here you see the definition of the conditional event probability. That's one thing that you see. The second thing that you see here, if I move this denominator to the left side, I'll move it to the left side. What do I have? I have PA times PB equals PA intersection B. So we have that formula from the definition of the event independence. So now I hope that you have some intuitive idea why do we use this definition for events independence. Yes, it looks a little bit obscure and with all that multiplications and so on, but you should think about it like when one event is happening, you are not getting any information on any other events that are independent from it. One more subtle notion, events can be not just independent, they can be conditionally independent. What it means that you can find some sort of condition or some third event C that will cut out of your space some part and will make your events independent. Okay, I will draw some small picture of it. Let's get more pictures, more intuitive ideas. I think it's good. So let me consider some overall space omega. And let me draw event A like this. And let me draw event B, let's say like this. So I have some parts here and some parts in here. So here you see that we have a very large intersection between events A and B that makes them dependent. Just from the intuitive point of view, if you have a very large intersection compared to the events themselves, you can probably guess that when one event happens, it makes a very big chance that the other one happened. But now I can use some sort of event C and cut out a small part, let's say in here, and just shrink to the consideration of this small part. And I can cut out this part in such a way that I have this condition to be fulfilled. So I will not get some additional information from one event or another. I'm just throwing away all this part of a big intersection. I'm just removing that, and I'm leaving only a tiny part somewhere in here. So that means that your events can be dependent overall, but you can find some sort of condition and cut out a small part of that big space, of that big sigma algebra. You can cut out a small part, and you will make these events independent by applying that condition. Okay. What else do I have? Condition. Yes, I told you that conditioning may affect independence, so that's good. Of course, you can make events dependent by choosing conditions some other way, in some cases at least. So that depends. A collection of events is independent if any uncollection is independent. Here is some formal definition, but you might guess where does it come from. just some sort of extension of our definitions for two events. Nothing fancy here. Pairwise independent events may be not independent altogether. That may happen. Here is an example of coin tosses. And if we are considering events like event A1, it's coin toss, the events of having heads when we are tossing a coin for the first time. A2 is event of having heads when we are tossing the second time, and these events are independent. And event A3 is the case when both coin tosses we have or either two heads or two tails. So that depends. They all are pairwise independent, and you can check that, that they are pairwise independent. But all three together, they are not independent. So please be careful. If your events are pairwise independent, it doesn't mean that they all are independent. So that may happen. Random variable, I told you about that. Few words about distributions. Okay, how much time do we have?
20 minutes.
20 minutes. Okay, I'm just thinking, should I skip this part or not? Okay, I will very briefly get through that, so hopefully we will have time to do something more before the break. Random, okay, I told you already that random variable should be distinguished from its realization. That's okay. So don't mess up with distributions with let's say distributions and PDF, so probability density functions. That's not the same thing. So if you have a distribution, a normal distribution, it's something, it's a variable that it generates you some numbers. But probability distribution function, it's just a method of describing it. So please note, so here is how do we note the normal distribution. So it's random variable x, and here is normal distribution n with parameters mu and sigma. And for normal distribution, we may have some probability distribution function. Here is p of x equals small x. And you have this famous formula with exponent and so on and so forth. And please note that here x small x is the realization of a random variable big X. It may sound for you a bit strange. Why do I may want to make that distinction between distributions and probability distribution function? And the thing is that you may have the same distribution, but you may describe it in different ways. You may describe it with probability distribution function or PDF. Or you can describe it with, let's say, cumulative distribution function or CDF, or you may find something else, but everything that will describe you the same probability distribution. So that's, let's say, a good point to
Excuse
know.
me.
Yes,
I
yes,
do have a
please.
question about notation, so a little bit upper. When we define that x is a normal random variable, and then the next formula, is it the probability that capital X random variable is equal to some value small x?
Here x is a realization, realization of random variable. So remember, a random variable x, that was a function that mapped me from my set omega into a real line.
Yes, but for continuous random variable, such probability of x capital obtaining some particular value x is always 0 because it's a continuous random variable.
probability, but not density of the probability.
I know, but I just so there is where comes my question about the notation. Why do we use the probability of x equals x here? If it's a PDF, okay, fine, let's use notation,
yes.
but why do we use the probability?
Well, maybe I should have used here some, I don't know, not capital P, but small p or something like that.
Like formula below,
but here,
you use the notion for density function that is like a small p sub big X.
yes.
That's the density function of random variable X, and it just describes how our random variable behaves.
Well, depending on the books, you may have different notations, so maybe this one is not the best choice. But yeah, it's I meant the same thing as this one, so that's a density of the probability, and it is defined as some sort of measure that you have.
Yeah, but I don't believe it can be just be equal to some probability of big X equals small x. It really just happens in some books that they do write some stuff, and it just
yeah, maybe
let's say it disagrees with other books and other definitions.
Yeah, maybe
because this is just a rule of thumb for continuous random variable. Each probability of it obtaining some one particular value is zero, because like this one dot has the measure zero on the real line. That's why the probability is always zero.
Yeah.
If we want to talk
I
about
agree.
measure
So
zero
probably,
perspective.
yeah, probably I should remove this one and more use like this definition. So that that depends on
this question about notation. Yeah, thanks.
Yeah. Okay. So probably I will change that, but hopefully you all get the idea that I mean the probability density function, and here is it's some sort of how you write that for normal distribution, and we will use that a lot. Okay, so we may have cases when we may want to we can describe, let's say, different distributions in different ways, and the same distribution we can describe in different ways. So, for example, with PDF or with CDF, that depends. Let's say I want you to appreciate the CDF because it's often like I don't know, it falls from our side that we can describe functions with CDFs, but it's really a powerful technique because you may have some distributions that you cannot describe with PDF, but you can describe them with CDF. Some sort of distributions that are, let's say, not continuous and not discrete. They are not that and not that. And you are still able to describe them in terms of CDF, but you can describe them in terms of PDF because they are not continuous. So please don't underestimate the power of the CDF. And in, let's say, many theorems, you will probably see in their proofs some sort of usage of that CDFs. Regarding discrete and continuous, of course, so we will not get into such a complicated things like distributions that are not discrete, not continuous, but we will probably see discrete and continuous distributions in our course. And regarding discrete distributions, I want to give you such term as probability mass function, or PMF. So in case you have a discrete distribution, you can use some sort of analogy to PDF, to probability distribution function, but you call that probability mass function. That is defined on a discrete set, and in this case, it gives you the exact probability of the event happening. So it's not more, let's say, density, but it's the definite probability when you are talking about all that discrete sets. Okay, so CDF is not redundant. So I told you it can describe distributions that are neither discrete nor continuous, and it can be used to find distributions y equals g of x, and that's really crucial in case of non-monotonic g. So it's not needed for monotonic G. You can find that with different methods, with PDFs, for example. But you can find this thing with usage of CDF. So it's one of very useful, let's say, techniques for you in case you are doing some sort of probability theory. Okay, so the defining property of a random process, so that's basically a probability distribution function. I will show you a few of them very quickly. So most PDFs you will see, they will consist, let's say, from two parts. So one part you can call it a functional part, so it really does something. And the other part is some sort of quotient that is used just for the normalization of whatever you have, because you want your function to be integrated into one. So So in many cases, we will have some distributions in form of some quotients, so x in some x, some e, and so on and so forth. Okay, please note that parameters of the distribution may not have a really nice and clear meaning like we have for normal distribution. So we all used to normal distribution, we really like it, and the thing that we like the most is that we can interpret its parameter very nice and clearly. So we can say that mu is some sort of mean value, we say that sigma is connected to that variance, and so on and so forth. But in case of different distributions, we may not have that, and you can even think about I don't know, reparameterizing your distribution function. And at the end of the day, you have some different PDF with different parameters, and they will not have any, let's say, clear meaning. So maybe that's a point for you to notice. So if you are trying to fit some points with some sort of distribution function, you may notice that parameters you have in that function, in some cases, they have some nice meaning and you can interpret them. In some other cases, they don't. Okay, so what else do I have? There are functions defined for random variable x that describe its behavior. And I want to show you a few such functions. So here is the expected value. So for continuous distribution, you are sort of integrating that probability distribution function with x, and for discrete, you are adding up, and you multiply xi by pi. So this is the expected value for some sort of probability distribution that I draw here. Okay, you may have different functions there. We will have a lecture on statistics, and probably I will show you some more. But for now, let's stay here. Okay. One more picture for you. Of course, I'm not getting through all this information, and don't think it's not to scare you. It's rather to tell you that we have very many distributions. So whatever are your needs, whatever you are doing, you will probably find something suitable for you. So it's not to scare you, but that's a little bit to cheer you up. So if you are doing some problem and you are trying to find some nice function, some nice distribution that describes results of your experiment or whatever you're doing, we have a lot of distributions, and probably you will find something that fits your needs. So there's really a big choice. Okay, two more well, about discrete continuous distributions, I already told you. One more term, like univariate or multivariate distribution. That just means that you have one variable in your distribution or you have multiple variables. Okay, few more interesting models for distributions. I will just really quickly get through the things, and then we will, I guess, then we'll make a break. But just a quick run. So an interesting model was picking balls from a sack. So you have so suppose you have a sack with n balls. You have, let's say, k red balls and n minus k blue balls. And you have some sort of probability of getting a ball from a sack, and you can calculate that as k divided by n. So you suppose that getting any ball from the sack has equal probability. That's a very interesting part I want to emphasize for you. So when we are describing some probabilistic things, there is always a moment when we prescribe some measures or some probabilities to the elementary outcomes and so on. So it happens somewhere. So you can deduce that. You are always putting that by your own hands into the model. It may seem very natural for you that when I'm tossing a coin, I'm getting, let's say, tails or heads with probability 1/2. That may seem very intuitive for you, but actually that's put from the outside. And when I'm tossing the coin, I'm telling to you, I'm tossing the good coin, and it has probabilities 1/2 and 1/2. It does not come out from somewhere. I'm just putting that in there by my own hands. And in some cases, this misunderstanding may lead to some sort of paradoxes or pseudo-paradoxes, and definitely some confusion. For example, if you are thinking about the coin that you have flipped, for example, 100 times, and each time you got some, let's say, heads, and then you are asking what is the probability of getting tails after flipping a coin 100 times and getting heads. And in some cases, people say that, well, we have a very large probability of having tails right now because we had a long series of heads. But it's not. First of all, you should return to the beginning and ask yourself, what's your model? And if you are thinking, well, I had a model of a fair coin, and I have, by hands, I put into there the assumption that there is 1/2 probability of having heads and 1/2 probability of having tails, why should it change after 100 flips? If it did not change, you still have 1/2 and 1/2. So that's a really nice point of confusion. So please remember, whatever you are doing with all that probabilities, there's always some point in time when you are putting that probabilities in there by your own hands, when you are crafting that model. So don't forget about it. Don't think that it's something that will come out from some outer space. You are putting it into there, and you should always keep track of all the assumptions that you are doing. So at this point, I'm doing an assumption that getting out any ball from a sack has equal probability. So if there are n balls, I have 1/n probability of getting a ball, but I'm putting that into there by my own hands. I can put in there some different assumption. So for example, some balls can be smooth and some can be rough. So I can feel which ball I am taking from the sack, and I can some sort of change probabilities. So like, for example, I like more smooth balls than rough balls. So I will try to get some smooth ball and get more probability of getting that from the sack. So it may happen. Okay, so and the second thing, the second trap you can fall into when we don't have any information on the process, we are inclined to think that everything has equal probability. It's not always the case. So if you are studying some sort of physical process, of course, it's the simplest model that you can assume, just prescribing equal probabilities to all elementary outcomes. But of course, if you are studying some sort of physics and so on, it may happen that the process you are studying, there is something happening internally, and you don't have equal probabilities of getting your elementary outcomes. So maybe you should perform some more measurements or get some more insights into that process. So maybe your model will have some sort of difference with what is happening in the reality. So don't fall into that trap as well. Okay. So back to this thing. So this model of getting balls out of the thag, it helps us to describe a few very useful probabilities, and I will show them to you right now. So of course they are discrete because our elementary outcomes are discrete, just getting a ball. So what can we have? What can happen with all that balls of thag? I am getting a ball from there. I can do one trial. So just once I can get a ball and look at it, and I'll have some result. I can do n trials. So I can get n balls from the thag. And I can do that with a so-called replacement or without replacement. So two more terms for you. If I am doing this experiment, let's say with replacement, it means that after I have looked on the ball, I put it back. So I still have some probability of getting it once again from the thag. Or I can throw it away and it never returns to the thag, and that's why I can never get it the second time. Or one more interesting thing, I can do some trials until I get, let's say, R successes or R failures, so whatever you call them. So for example, I'm trying to get balls from the thag until I get 3 red balls. And in that case, I'll be asking how many balls did I get from the thag before I was able to reach that number of 3 red balls. What do I have in these cases? When I'm doing one trial, so independently, am I thinking with replacement or without, I have a Bernoulli distribution. Well, replacement does not matter because I'm just getting it one time, and it doesn't matter whether I throw it away or I put it back into the thag. I will not do anything to that anymore. When doing n trials, I will get binomial distribution with replacement, of course, and with replacement, when I'm trying until some R failures, I will get hypergeometric distribution. If we are doing the same things without replacement, we will get, well, basically something similar names, let's say, different distributions. I will show you the formulae in a bit. But we have them with name negative. So if you hear negative binomial, you should instantly note that you are doing all the trials without replacement. So you can think of getting some balls out of some thag, and you throw them away. If you hear negative hypergeometric, then it's until R failures, but without any replacement. If there is no word negative, you have that with replacement. Of course, Bernoulli or negative Bernoulli, they are all equal, so it doesn't matter. So what is Bernoulli? One trial, you have one result. Either you have, let's say, with probability P result 1, or with 1 minus P, you have result 0. Nothing fancy here. Expected value and variance you see here. Binomial distribution. You are performing that tests. So remember, binomial, there is no word negative, so we are doing with replacement. I'm taking out the ball of the thag, I'm looking at it, and I'm putting it back. Then I'm doing second trial, third trial, so on and so forth. So here is the formula for this distribution. So you are basically doing a sequence of n independent experiments. Each time you are asking a yes/no question, and each with its own Boolean valued outcome. So you may call them success, yes, true, 1 with probability P, and failure, no, false, 0 with probability 1 minus P. So a single success failure experiment is also called a Bernoulli trial. So it's a series of Bernoulli trials. So here is a tree of that binomial distribution. So you are performing that experiments, and at each point, at each vertex of this tree, you have two edges coming out of that, and that means that you have performed your experiment and you have either success or you have failure. At the end of the day, we are interested in the total number of successes and failures that we had in our experiments. And you might guess that if I'm interested, for example, in 2 successes, 1 failure, there are many ways I can get to that result. So here, a few of them are here. They are shown. So you have the probability of getting through this tree. So you remember, when I'm having success, it's probability P. Then to have 1 more success, it's 1 more multiplying by P, so P squared. Then I should have a failure. I'm multiplying by 1 minus P. And this term is everywhere equal. But the number of possible outcomes should be counted with some sort of combinatorics. And you have this quotient 3, 2. Here you have mean and variance. That's quite simple. Here is a small demo for you that draws the distribution. So here are a number of successes and probability. It's discrete. So you have these points, like, think about them like discrete points. I just joined them with lines to make them better visible. You can change parameters, so you can see how it changes, and you can change number of samples to see how the histogram comes closer or further from the distribution we have. Of course, the more points, the more number of samples we have, the better it fits. Negative binomial. It's a discrete probability distribution of the number of successes in a sequence of independent and identically distributed Bernoulli trials before a specified, a non-random, you should specify it, number of failures that are denoted by R. Why it's called negative binomial? Here is the formula that explains that to you. So here is the distribution. You see this quotient K plus R minus 1, and you can think about it like some sort of binomial quotient, but just with negative R here. Double brackets are also called Stanley's symbol, so you may want to check that in Wikipedia to get some more ideas about these things. Well, if you feel interested in that. Here is mean value and variance. As you see, it's different from the non-negative binomial distribution. Hypergeometric distribution gets even more complicated. So you are counting K number of red balls when drawn from the set of that has K red balls and N minus K blue balls. You are doing that. Here is the formula, and you have its mean and variance. It's even too complicated to write it down, so just know that it is. And here is a negative hypergeometric distribution. Once again, you are doing the same thing, but you are doing without replacement. So there we had with replacement, here we have without replacement, and once again, you get this formula. So not getting into that, but you should just know that we have these models, we have that formulae, and if you need that, if you can reduce some problem you are studying to that model with balls and SEC, you can do that. Multinomial distribution, just showing you a formula, nothing fancy here. This is some sort of modification of that quotient, combinations of NK. So here we have a bit more complicated formula, and you may guess that these are the probabilities you are multiplying. Simple expression for mean value and variance. Poisson process, very loved by physicists, and in Q theory, It arises from some sort of random process that moves through some number of states. So you have state 0, you have some probability flow described by lambda, and you can get from that Poisson distribution. It's used very widely in telecommunication, in astronomy, chemistry, biology, and many other things. So even in radioactivity, you have number of decays in a given time interval. It's described with Poisson distribution. Here you have its mean and variance. You see that they are equal. Very unique distribution with this feature that mean is equal to variance. Distributions with mean less than variance are often called over dispersed when they are under dispersed if mean is greater than variance. And you can view that as a limit of binomial distribution when n is getting to the infinity, but you are keeping track of the n times p, so n times probability. You are getting more and more n, but you are decreasing the probability, and you are doing that in a way that it remains constant. And this constant is called lambda, and you use that in your formula for Poisson distribution. Here is some sort of demo for you. Once again, you can play with it when you have some time, so you can see how the histogram fits that distribution when we are changing number of samples. Some continuous distributions very quickly. Uniform distribution. Well, almost nothing to say. Very simple mean and variance. And by the way, the variance of a uniform distribution coincides with the moment of inertia of a solid rod. So, so physicists may think for a moment why. Exponential distribution. Very simple distribution. It governs, for example, some radioactive decay or density distribution in a uniform gravitational field or capacitor discharge and some other physical processes. So physicists should love it. And here we have a mean and variance for that distribution. And here we have, once again, some plot and some histogram that you can check whether it coincides or not and when it does. The most beloved distribution, Gaussian or normal distribution. I don't even remind you about all that formulae. You should remember that thing. I'll just tell you that, well, maybe the biggest source of our love to that normal distribution is so-called central limit theorem. And it tells you if you have some random variables x, you have many of them, they are independent, identically distributed. So that's very crucial. I will remind you that term when we get to statistics, but I want you to remember this IID, identically independent, identically distributed. That means that each xi has the same distribution and they all are independent. So whenever one happens, it does not influence and does not some sort of disclose some information on the other. You can collect these sort of formulae. So they have finite mean and variance. And if you are writing this sort of formulae, you are extracting that mean, you are dividing by square root of n variance, and so on. You have in the limit, you have probability of getting this thing smaller than some number z. The same, you have probability of getting normal distribution smaller as some number z. A bit of maybe cumbersome method to write this thing, but it's mathematically rigorous, and that's the way that you write it. And of course, you may notice that the letter is CDF. So cumulative distribution function. You are getting some number and you are asking about the probability of getting something smaller than that number. Of course, it's cumulative distribution function. So once again, don't underestimate CDF, because when you are stating in the central limit theorem in the most, let's say, general form, you are using CDF. Okay, so it's very universal, normal distribution, very universal and easy to apply. It has only two parameters, means and variance, with clear, distinct meaning. It's fairly accurate and computational shortcut, and this central limit theorem is some sort of justification of normal models. So in many cases, you may want to employ that. One more example of plotting that for you. So you can change mean, you can change variance, you can change number of samples, and you can see what happens to all these functions. Many different distributions. I showed you the whole image with that distributions. So I'm not getting into that. Instead, what I want you to say, for example, one is so-called Pareto distribution. So maybe you heard the such sort of like fact that 20% of doing something makes you 80% of success. It comes from some processes with the Pareto distribution. It describes some sort of, for example, allocation of wealth among individuals, some sizes of human settlements, and so on and so forth, and it's notorious that this rule 80-20, it can be derived for variables that are following Pareto distribution. So if something is following that distribution, you have that some sort of rule. Okay, I think with that being said, we can make a small break, and then we will get to bias. Okay, let's continue. So the main point of this lecture is, let's say, bias theorem. So I want to talk a few words about bias theorem and tell you why do we need that, and well, what's going on. So we were talking about probability. You might guess that we may have different approaches to defining the probability and to all that probability problems at all. The first approach that we all study at school is, let's say, approach based on frequencies. So when we are treating some sort of probabilities, when we are treating probabilities like some sort of frequencies of occurring some events in a series of different trials. It's easy to grasp. So, for example, you can think about tossing a coin or rolling a dice, and you are thinking that when I'm rolling a dice for 1 million times, I will have 1/6 number of that rolls will result in, let's say, having number of 6, and 1/6 of that rolls will result in having number of 5, and so on and so forth. It's very, let's say, naive approach. And if you think about it, it's really, first of all, it's not rigorous. And the second problem is that you cannot always talk about events and probabilities in terms of frequencies of their occurrence. So you may not have the ability of perform some experiment for more than one times, but you still want to talk about some sort of probabilities. The second approach is a very rigorous approach made, I guess, by Kolmogorov. And we basically went through that approach at the beginning of this lecture. So all that measures, functions, sigma algebras, so on and so forth, that's the second very rigorous approach. But you may have a third approach to the probability. It's called a Bayesian approach, and that is based on the Bayes theorem. So in some sense, you are saying that you are exploring some sort of process, and the probabilities are not like predefined, like in Kolmogorov's approach or somewhere else, but you are getting them from the experiment and from the data that you are collecting. So you are performing, for example, you are tossing a coin, and while observing the results of that process, you are continuously updating your ideas about what is the probability of getting heads and what is the probability of having tails. And that is based on the Bayes theorem. And you can see that approach in some cases and even in some works. And probably what we will be doing is some sort close to that approach. I mean, to the idea of performing some experiments, saying, well, I have some results, they are some sort of random, but I can't predefine their probabilities. I want to get them from the experiments that I am performing. But it's not like in an approach with frequencies when you are just calculating your frequencies, but you are using Bayes theorem. So it means you are defining at the first step, you are defining some approximation of that frequencies, and then you are updating that approximation with Bayes theorem. So we'll get to that, but I just want you to see the whole way. So we are going through that way, and we will try to update some probabilities based on the experiments with Bayes theorem. So now, what is the Bayes theorem, and how do we use that? The idea is as follows. I'll draw that really quickly. So let's consider the joint event. For example, I have A and B happening at the same time. What is the probability of events A and B happening at the same time, considering them from the point of view of conditional probabilities? So let me draw you a picture first. So here's my overall space omega. I have event A, and I have event B. Okay, not very clearly seen, I guess. And I'm asking a question about this part. So what is that? So if I am talking about probabilities, I would say that it's probability of A and B. Now, depending on how you look on that, you can get in either one way or another way. So one way you can tell, okay, suppose that I am considering this probability as that A happens when B happens. So I know that B happened, for example, and now I'm considering just some sort of sub-event of happening A when B. So that is the probability that event B happened, and then you can say that A happened given B. On the other hand, you can think about it like event A happened, and then you are considering this small part. And when you are considering this equation, you can get the result. I'm just taking this part, I'm moving this PB to the other side, and I'm getting PA condition B is equal to PB condition A times PA divided by PB. And here you have the Bayes theorem, so the Bayes rule. In, let's say, plain words, it helps us to change places these A and B. So if I have A condition B, I can swap them and talk about A condition B in terms of B condition A, and we will use that just in a moment. So we will need that. Here is an example of usage of that theorem. I won't get into all that calculations. I'm sorry, we don't have time. Just the general idea. So here are two, for example, two jars, and in one jar you have, in each of these jars you have red and white balls, and you are taking out one ball from some jar, and you want to know from which jar did you took that ball. So to make it a little bit more intuitive, so let me draw that again. So here I have two jars, and I have some balls in here. And I want to talk about the, and I don't know from which jar did I took the ball. So for example, it was, I don't know, in some dark room. And I want to guess, was it jar number 1 or number 2? And depending on the balls in here, I can get some information. And Bayes' theorem will give me that information. How much information do I get? Depends on the contents of these jars. If one of them contains only, let's say, black balls, because I have black pen and blue pen, so the other one contains only blue balls. This is very nice situation. If I got a black ball, I'm sure that I got it from the jar number 1. If I got a blue ball, I'm sure I got it from the jar number 2. So I have definite information from where did I get this ball. But if I have some sort of mix of that balls in both jars, that may happen that I got a black ball, but I got it from jar number 2, or I got a blue ball, I got it from jar number 1. But you might guess, I want you to have some sort of intuition on that. So once more, so getting more intuitive about it. If you see the concentrations of these balls in the jars, you might guess that depending on that concentration, you may be more or less sure that you got, for example, your black ball from jar number 1. If I have a perfect separation, so no blue balls in jar number 1, no black balls in jar number 2, that's perfect separation. So looking at the color, I'm definitely know where did I get it from. If there is some sort of mix, depending on that mix, I can get some information. If I have one blue ball and 100 black balls here, then, and one, for example, black ball and 100 blue balls here, when taking a ball out of there, I'm almost certain where did I get it from. If I have a mixture 50-50% in both jars, or I have some sort of equal mixtures with equal number of percents in both of these jars, I don't get any information. So whatever I take from the jar, it doesn't tell me anything. And the amount of the information I get from there is basically measured with Bayes' theorem. So how certain you are that you took that ball from one of the jars. So it's some sort of measure of that information. And it will measure for you that certainty in many other cases. Here is one. Here are a few more terms for you. So I wrote for you the Bayes theorem, and here are terms like prior. That's the probability you had before starting your experiment. It's, for example, P of A. Likelihood is the probability of A given B. The posterior probability, it's what you are aiming for, is the result of the Bayes formula. And the evidence or marginal likelihood function or integrated likelihood, that's P of B. So we will see that in a moment. One more problem that is solved with bias theorem is so-called Monty-Hall problem.
Apologies, I guess there is a little typo up there. So if I guess likelihood then must be P probability of B with the condition of A, because it's the same as a posterior probability.
Posterior.
So what is the event
yes.
that we are? What's the event and what's the condition here? A or B?
Yes. You're right. You're right. So I'm multiplying PA. It should be P and B. Okay, I don't know how to switch PB given A, I guess. Should be that way, probably.
So that's our event A that we are looking at. Then something called B happens. We get the posterior probability of A happening after B happened. And we would like to get the likelihood. So what was the probability of event B happening prior to the event A happening?
We want to have the posterior. This is the result we're aiming for. So A, when the condition B is met. Okay, maybe I messed something up here.
The evidence, I guess, must be probability of A.
Yeah, so if it's PAB, then yeah, there should be A down here and A down and A up. Okay, probably this is more correct, yeah? So PAB times...
prior times likelihood, PB times PAB then?
No, prior should be A. PBA times PA, that's the probability of B and A.
Intersection B, and then we divide it by...
Evidence should be PB.
B. So we divide it by probability B, and we get posterior A with the condition of B.
Yeah, that looks
now
right.
It's working. Thank you.
Yeah. Okay. So Monty-Hall problem. One more problem that you can solve with bias theorem, and that seems a little bit counterintuitive at the first glance. So here is an example for you. So you have 3 doors. And I am like proposing to you that you may, that you have, I don't know, I have some price behind one of these doors. And I am proposing to you a chance to win that prize by choosing the correct doors. And and maybe when you are trying to choose the doors, you don't have any additional information, so it basically doesn't really matter which door to choose. So for example, you choose the rightmost door. At that moment, I am doing the following thing. I'm opening one of the remaining 2 doors, and I'm showing you that there's nothing interesting there, so there is no price. And you have a choice. You can still stick to your first choice and say, well, I am expecting to have price behind these doors, or you can choose to swap to the different door and check for the price right there. And there is such an interesting counterintuitive question. How do you think, is it beneficial to change your decision, or it doesn't really matter which door you choose? So can anyone just quickly from the intuitive point of view, like say that I will stay, I will swap?
Beneficial, it's beneficial.
Yeah, that's beneficial. Yes, you're right. So it's really beneficial to change your mind, because that in most cases, like 66%, you will get your price. So you have some additional additional probability. It's even you can find this problem in popular culture. So I'm sorry, I don't have time to show you this small video, but you can check later. It's I guess film 21 or something like that, and you can check a small scene from there that uses this problem. And here is how do you solve that with Bayes theorem. So you can use Bayes theorem and, well, explain to yourself that you really have a 2/3 of probability of gaining the prize if your, let's say, strategy is to choose the door and then change your decision when I open the door that has no price. Okay, now let's get a little bit closer to machine learning and talk about classification problem. So this is a problem. It can be binary or multi-class classification. I guess I will show you examples. I will definitely show you binary example, not sure about multi-class right now. That's the case of supervised learning. And it may be, in some cases, it may be more or less complicated. So we are getting to so-called naive Bayes classification. So first of all, there can be different modification of this classification. For example, normal or Gaussian, I guess, Bayes, multinomial, or Bernoulli Bayes. So that depends on the probability distribution that you are considering. So I told you, we are talking right now about a so-called generative model. So somewhere there behind these stages, you will get some sort of probability distribution function. But you can just ask for any probability distribution function because there are too many of them. So you are restricting yourself to some family of probability distribution functions, because when I'm talking about normal distribution, that's basically a family, unless you define exactly that mean value and that sigma, that mu, and so on. So if you define them, yeah, you have very definite PDF. But if you don't, you have a number of different PDFs that you can change when changing that parameters. So we are restricting ourselves to one of the models, and we use that formula to get, let's say, some result. Before we are getting into that, I will show you an example of classification, let's say, spam filter that we can do basically by hands. And I will try to explain you some sort of ideas that stand behind this filtering and why do we need all that, let's say, details. Here is an interesting image for you. So probably you know that term spam comes from interesting group called Monty Python. So maybe you have even seen some sketches of them. If not, you should definitely check. There are really nice things, for example, like Parrot No More and so on. And they have a sketch about spam. And we all don't want spam, but sometimes there is no choice, as you see in these menus. So everything comes with spam. Okay, so let's get to filtering. So I have a bunch of letters. So this is supervised learning. So I have some sort of data set, and I'm doing something with that data set. And this data set is labeled. So I have some letters, and some of them are designated as spam. So that's the letters I didn't want to have. What are we doing now? So first of all, what do we need? We need some features. So when we are exploring some machine learning problem, the first question we ask, what are the features? Because from the features, we will construct our data points. Let's consider just one feature. That's the word by if whether you have it in the data set or you don't. So your feature can have just two values, 0 or 1, that depends on whether you have that word in there or you don't have it. And you want to build, on top of that, you want to build some sort of classifier. How do we approach that from the naive point of view? What I want to have is when I'm getting, so let's draw that again. Let's start with some very naive implementation without usage of bias, and then we get to that bias thing and understand why do we need it. So I have a data set. So I have a bunch of letters that are marked as spam and that either contain word by or they don't. So I have some spam in here and I have a lot of that letters and I can do something with them. And I have not spam. Some more letters. If I am basing on the existence of word by in these letters, what should I do to build a classifier that will tell me the probability that the letter that I become, some new letter, whether it's spam or it's not spam? Well, the most naive way, basically, it's to check how many letters in here contain that word, how many letters in here contain that word, and that brings me some idea where should I put this letter, whether it contains that word or not. So what are these probabilities? So for example, this is my class, let's call it C for brevity. So the probability of a letter being in class C when I have a word by in there. So I have that word. And here is some complementary probability of being not in class C if I don't have a word by in it. That's quite simple. So you can calculate that, you can do that. But now, why do we need bias? The things become more complicated when you get some more features in here. So for example, I don't want to just base on one word that is in the letter. I want to consider some more words. So for example, I don't know, some buy and some $1 million and some other keywords that I want to use to filter spam. So I'm getting more and more words. What should I do? Do I calculate the probability of class C that contains some word, I don't know, some word 1, word 2, word 3, and so on? Can I calculate that? In principle, it looks like possible. Yeah, so what prevents me from doing the same thing as with one word? But let's consider a bit different aspect of this problem. How large should be the data set that I'm using to calculate this thing for n words? I can either have a word in there or I can not have it. So at each of these places, I'm basically putting 0 or 1. So I can have a word or I cannot have a word. If I have n number of them, what is the number of possible conditions in here.
2 to the power n?
Yes. So I have 2 to the power of n. That's a very large number. If I have, for example, 1,000 words that I want to use for my spam filtering, I am in troubles. Because 2 to the power of 1,000, you remember that 2 to the power of 10 is something like 1,024. So 10 to the 3 approximately. So it will be 10 to the 300. That's a very large amount. And that's only to probe one point with that. And if I want some relevant statistics, I need at least, I don't know, 100, maybe 1,000 points for each case. That makes things even worse. So if I'm having a lot of words, I cannot go the exact direct way and just collect spam, non-spam, and calculate all these things. That's not the way it works. Okay, then you might ask me, what do we do in this case? In this case, we use two things. We use Bayes theorem. That's the one thing. But it doesn't look for the first glance, it may not look like very helpful. So what do? I'm trying to rotate this W1, W2, and so on to Wn. I'm trying to rewrite that with Bayes theorem. So what should I write? So the probability of getting these words class C, then what else? So I'm multiplying by probability of class C, and I am dividing by probability of having that words. It may look like nothing good happened. Yeah, so I still have this problem of many words. But right now, one thing comes into the play that we didn't use before. What happens if I assume that seeing one of these words, these events of seeing word Wi from some word Wj, they are independent? What happens to these formulae? So right now I'm doing one more assumption. So I just used Bayes theorem. Nothing like changed. But I'm saying one big thing changed. Now I'm able to do an assumption about the independence of these events. What can I do with this formula? Any ideas? What means independence? Yes, please.
Probably rewrite it to break the probabilities.
So I can rewrite this as what?
Multiplication?
As union.
Yes, multiplication as a product of probabilities.
Yes.
So that's the main idea. So I can write the thing when I assume the independence. So I assume independence and I can write this as the product of PW1 condition C, PW2 condition C, and so on to PWN condition C. Oh, I guess I should use capital N, yeah? And now it's my question for you. So in here, I was obliged to keep track of 2 to the power of n of different numbers And I should get these numbers from some sort of statistics. How many numbers do I need here in this approach? Basically, yes. Because any combinations of these W1, W2, and so on, well, it's a bit more, let's say, complicated, because you may have 0 or 1 in here. You can have 0 or 1 in here, and so on, 0 or 1 in here. So for each W, I keep like maybe probability of 0 and 1, or maybe I'm doing 1 minus that, doesn't really matter. But at the end of the day, I can multiply them depending on the combination of words that I see. I don't need to track all the combinations. Like in here, I'm just tracking the individual probabilities, and then I'm multiplying them to get the overall probability. This is basically the explanation why you will never hear about method of bias without telling naive bias. So why bias is naive? This is naivety. So this assumption that we have independent probabilities for getting each of these words or each of these features when you are studying something else, that gives your bias the word naive. It helps us to overcome the problem of getting too much data, or that we need too many these probabilities. But of course, it gets with the cost of making that assumption of independence. And in practice, one of the, let's say, biggest flaws of naive bias is the fact that in practice you rarely have that probabilities independent. So that may be a problem. On the other hand, what can you do? Without that assumption, you will have this kind of problem. And to make things even more intuitive for you, of course, this formula needs some sort of refinement, just a little bit. So you should ask, of course, yourself, how do you get this part, like probability of class C? So you should have some prior probabilities of having some classes, and you should never neglect that probabilities. So never neglect your priors. They matter. They matter very, very much. As a simple, as the first simple example, for example, you are creating some system that is, I don't know, detecting terrorists. And if it sees some terrorist, it, I don't know, rings a bell. And your system is let's say, so if there is a 10% chance, or I don't know, no, let's say 1% chance that it will detect some regular human as a terrorist, and 1% chance that it will detect terrorist as a regular human. So is this system good? So how good is it? So you're saying no.
Oh. Because
yes,
it's
no,
very bad
because
if terrorists treated as human, as normal.
no, it's actually worse that we classify regular people as terrorists, because there are much more, many more of them.
Yes.
So we will get a lot of regular people classified as in the class of terrorists.
Yes, you are absolutely correct. So that's the problem. So the prior is the problem. If we are talking about some regular city, you may expect that you have much more regular people than some sort of terrorists. So you have 1 million of regular people and, for example, 100 terrorists. And if you think about this system, if you make it to look at each one in this city, you will have 1% of that 1 million people to be classified as terrorists, and only 99 terrorists classified as terrorists. So of course, if you calculate the probabilities, if you hear that bell rings, it doesn't mean anything. It's much more probable that it's detecting some regular human as a terrorist, but not the other way around. So that's the problem. So please never forget about your priors. So we should have them, we should estimate them somehow. So of course, if we have some sort of data set, we will calculate how much spam, how much not spam we do have there. And we can calculate this probability, but please just don't forget about them. And this one is the probability of having that combination of words W1 to Wn. But you can calculate that as well, because you can rewrite that using all that assumptions that we had before. So you can write this as with class C and class not C, some of that probabilities, and how to calculate that probabilities you already know. So that's what we have in here. And the last thing to make these things even more intuitive for you, the last question, and we move further, is the question about this expression. So, so right now, I already know that expressions like PW1, well, let's take just W1 and W2, condition class C. You can write that as PW1 class C times PW2 class C, of course, assuming independence. So assuming independence. What about the expression P, the probability of class C, given the condition of words of W1 and W2? So I'm setting here a big question mark. And I'm asking, do we really need all that bias thing? Maybe we can get with some sort of naivety. Can I write something like this? How do you think?
Probably
so, okay,
no.
No, I cannot write that. And I want to give you some sort of example that shows you why can we not write that. So here's my space of events, and I'm dividing it into two equal parts with event W1 and not W1. So here is 0.5 and here is 0.5. Now event number 2, so having a word number 2 or not having it, let it be 50% as well. Now I need some classification, some class in here. Suppose my class coincides with the event W2. So here leaves my class C. Everything else is not C. And I'm building a classifier on top of that. So I'm doing some sort of classification. I will have a really nice classifier because one of my features, it basically distincts me class C. Now, can you tell me about these two events, W1 and W2? What about their dependence or independence? Dependent or independent? How do you say?
Probably independent.
Independent.
Yes, they are totally independent.
Like if W1 happens, we have no idea what is with W2 because it can happen or not happen.
With the same probability.
Actually, with the same probability, so it's...
Yeah, absolutely correct. So whether W1 happens and you have this part, you still have W2 50-50, or W1 does not happen, you still have 50-50, or W2 happens, you have W1 50-50, so on and so forth. So they are independent as much as they can be, so no dependence. Here is the class C that we are classifying. Now, let's get to these two formulae, and let's check what happens in here. So what is the probability of of having W1 and W2 in case of class C. So it's very simple. Where do we have events W1 and W2?
Top left
This
square.
Yes, this small quadrant. And what is the probability of this thing?
1/4.
Yes, it's it's 1/4 overall. Wait a moment. No.
The probability of just happening
given class C. But given the class C, so I have class C, it means I don't see this part. So now given the class C, what is the probability?
1/2.
Yes. So given class C
is like he doesn't live only in the top right corner.
Class C lives in here. So this is the part, this blue part is class C.
Okay, both top parts are class C. All right.
Yeah, so we have class C in here. So this means condition. So we are restricting ourselves to class C. And here we see that this part, it takes 1/2 of this rectangle.
Yes.
So we have 1/2. So that's everyone understands that, yeah? Good. Now let's get to this part of the formula. What is the probability of having W1 in case of class C? So once again, in case of class C, so I'm like not looking at this part. So this is my condition. It means that C happened already. So that's all. What is the probability for W1?
Again, 1/2.
Yes, that's 0.5. What about W2? Once again, condition C. And if you think
already
in the top part, so it's 1.
Yes, it's 1. Because class C perfectly coincides with W2. So if you have class C, you definitely have W2. If you have W2, you have definitely class C. So if you multiply these numbers, 0.5 and 1, you get 0.5. So Bayes' theorem works. The independence formula, it works. Now let's look at this formula and check what happens in the left side and in the right side. So in the left side, I have the probability of class C given W1 and W2. So now this is my condition. So I should cover up with these 3 parts, yeah? Now, what is the probability of class C?
The probability of being in the top part, given that we're in the top left corner, it's 1.
Yes. So probability of this blue thing when we are in this top left corner, because that is W1 and W2. So what is the probability?
1.
Yes.
1.
So we have 1. Now, what is the probability of class C given W1? So W1 is now my condition.
1/2.
Yes, 1/2, because I cover up this part and I have still 1/2 with class C. So this is 0.5. What is the probability of class C given W2? So now W2 is my condition. Why?
1?
1, yes, it's 1. It's 1. And here you might see that this formula works. 1/2 is really 1/2 times 1. This does not. 1 is not equal to 1/2 times 1. So you cannot split this sort of formula into parts. You cannot make it into multiplication, it does not work, but it works here. So this is the explanation why do you need Bayes formula and why do you want to make it naive. So if you don't make it naive, you are stuck with too many probabilities. You can't calculate that. You can't have so large data set. If you want to do something with that, you can assume that sort of naivety, the independence of them, but you cannot split this sort of formula. It doesn't help you. But if you use Bayes theorem on top of that, so you make a naive Bayes, you can reverse this thing, so bring these W's to the front, make this sort of formula, and this you can split into parts, and you can make a multiplication, and that saves the day. So that makes you able to calculate all that things. Okay, how much time do we have? None.
We finished already.
Okay. I guess so. Okay, I'll do that in 5 minutes to wrap up. So at this point, we have created some sort of simple spam classifier basing on the Bayes theorem. But the interesting part is that I want you to be aware of is the fact that we are doing some sort of assumptions regarding the probability distribution that we are using for our Bayes theorem. So as so let me remind you just a little bit that when we are calculating everything we want, we use like this sort of formulae, looking quite complicated. But anyway, whatever we do, we should have some idea. Let's take this simple example. We should have some idea how do our probabilities PA, PB in case of A and so on look like. And the problem is that when I'm posing to you such a simple question like classifying letters, just basing on the fact whether they do contain a word, let's say word by something or something like that, I'm in sense of oversimplifying the problem, and you immediately see how would you estimate that probabilities. But in the real life, it's more to that. So you should have some idea or some model or some probability model that will help you to estimate that probability distributions. You can gain some intuition when, for example, you will transfer from a very simple classifier that just took into account existence of some word in a letter or its absence to the classifier that, for example, counts how many times you have seen that word in a letter. And probably at this point you will think, well, I have this word, for example, 3 or 5 times or 6 times, and how can what can be the probability distribution behind that? Because you need that probability distribution to calculate Bayes formulae correctly. And things get even worse when you get to some sort of continuous distributions. So I have a feature. That feature is a real number. It can be any number, for example, I don't know, let's say from 0 to 1 or from minus to plus infinity, whatever. But whenever you get some value, you should somehow estimate what stays behind that values. In the following lectures, I will show you some general method of estimating that things when you have at least some idea about the family of distributions that may be behind the stages. It's called MLE, maximum likelihood estimation, so I will show you that. But at this point, let you just believe me that at least in case of normal distribution, you can do that estimation just by calculating the mean value of your feature and its variance, and then plug it into the Gaussian distribution. So here's an example of multi-dimensional Gaussian distribution for you. So you see how it looks like. You can see some points that are generated with this distribution. So that's what you get if you have I don't know, two features, and you are getting some data points. So you are collecting some data, and that's the data you have. And in some sense you can estimate how does this distribution look like. If you neglect one of the features, you get what you see there behind this Gaussian. It's some sort of marginal probability distribution that you have by integrating everything along these lines. If we are talking about some conditional probability, it looks a little bit similar, but you are just cutting through this two-dimensional Gaussian, and you are getting some sort of cut, and that will be your conditional probability. So if you have all these points, you can somehow estimate this probability distribution, and you can get your probabilities, be that conditional probabilities or marginal probabilities or whatever you need for your calculation. Here are some sort of reminders about the formulae. How can you analytically describe that function? So here you see matrix sigma, here you see mean values mu, and so on and so forth. So so these things become vectors because we are working in a multi-dimensional case. Sigma becomes a matrix. So here are some examples how that sigma influences sample data points. So I'm not drawing the exact curve, the exact distribution, but I'm showing you some samples that I can get from that distribution. And here are examples with a diagonal sigma matrix, or with sigma matrix that is diagonal but has different values on the diagonal, and so on and so forth. These values, you see you have some off-diagonal components to sigma matrix. It's always symmetrical, so this case is the most general one. And about this row that you see here, we will talk in the subsequent lectures. That's some sort of coefficient of correlation. Now what I want you to show are few examples, few demos that should at least partially make all these things intuitive for you. For example, consider some sort of experiment. So here I have two distributions, two normal distributions. I'm choosing them, well, somehow, so whatever. And this is the case I'm trying to use to build a classifier on top of that. So I'm trying to build a naive Bayes classifier. I'm supposing that I have two classes, red and blue, and moreover I'm supposing that whenever I'm drawing some data point from one or from the other of that classes, I'm just getting let's say some point right here. So let me draw some samples. So I draw a few samples from one class and from the other class. So here is what I have. On the x-axis you see these points, some red dots and some blue dots. This is my data set. So I have measured some feature. Feature goes along this x-axis. I know it for each of my data point, and each of my data point belongs to one of the classes. So we remember we have classification problem, that's supervised learning, and I know for each point which class it is, it belongs to. I should train some sort of classifier, and that classifier should be able to answer me regarding any other point. Should I treat it as a point of blue class or as a point from red class? What does the naive Bayes classifier do? So first of all, we recover somehow these probability distributions. So these solid lines, blue and red, are real distributions. We don't know them. We don't know them for sure. So let me hide them. These dashed lines are showing what I am basically trying to guess. So I'm having some data points and I'm trying to guess what is the form of that normal distribution that generated these points. In this case, I'm just using mean and variance from calculated from these points and plug it into the Gaussian function. The next lecture you will know why can I do that. Well, because of so-called maximum likelihood estimation, and that's really you can mathematically prove that this is the best choice of the parameters of that distributions. So here we have them. Having these distributions, I can calculate with the help of Bayes' theorem what is the probability of every point to be blue or red given value of the feature. So I'm having my data set. I am some sort of extracting these two distributions. They tell me if I have feature here on or there, what is the probability density to be generated by one or the other distribution. And I can calculate how do I treat all the rest points on this line. The interesting thing for you to notice that prior influences the result. If I have equal number of samples, let's say 2020, why can I make it 21, 20, 2020, you may see that this borderline that's basically splits me x-axis into two parts. The part where I treat all points as belonging to the red data the red class and point that belong to the blue class. It goes exactly through the points through the point where these two distribution intersect. But if I have some sort of different prior, for example, it is much more probable to have a red point. So let's make, I don't know, 50 red points and just 20 blue points. You see how this border, how it shifts. It shifts because now it's much more probable to have, 50 blue points and only 20 red points. Because now it's much more probable to get the blue point just prior to anything, whatever we calculate, than a red point. So I advise you to test this demo and try different setups, try different distributions, and see how this classifier works and how can look the result of its work. So you see here I have 3 regions instead of 2. So you may think for a while, how many regions can I have? Can I have 1 region? Can I have 2, 3, 4 regions? So whatever. Okay, so here is example for a 2-dimensional case. I am just skipping most of the part. What I want you to show it's one more demo. Here is the 2-dimensional demo that should calculate, let's say, all that Bayes thing based on a small data set. In this data set we have 2 features, so x and y. Here I am placing some points all around the plane. I can use many classes. Here everything is classified with sklearn. So I'm just putting data into sklearn naive Bayes. Here you see I have imported Gaussian NB. So my model is the Gaussian naive Bayes. And I have just simple interface like fit and predict that will predict me how should I classify all these points, and here you see the result. An interesting thing I always like to ask that I want you to think about: if I have a data set that looks like this, so points here, points here, points here, and I'm putting some points in here. So I want you to look at this result and to think for a moment what has happened here. This result looks like a little bit like a paradox, because now you see that really I have red points, and everything near that red point is classified as red, and green and blue and so on. But for these sort of violet points, there is a problem. The classifier classifies as violet everything outside these regions, but you see that there is no point of that color in the region that is classified as class D. So no point of class D in the region classified as class D. On the other hand, all points of class D are lying within regions that are prescribed to different classes A, B, and C. And the reason behind this is basically, if you think for a moment how this classifier works, and maybe even return for a moment to the one-dimensional case and understand what happens with all that normal distributions. So probably I'll draw that. So here we have so let's think in 3D. So here is my plane with my data set. We have feature 1 and we have feature 2. If I have a few points in here that are sitting closely to each other, I will definitely estimate the distribution that has generated these points as this sort of very spiky Gaussian function. So here how it looks like, something like that. The same way I will estimate this sort of distribution function if I have these points in different places. So for example, here is another class of points. So I'm drawing that with squares, and one more class I draw with some sort of circles. So here once again I'm having all these very spiky distributions. But now what happens if I will put into all this, inside of all these things, some sort of point of a very different class? I don't know, let me designate it with, I don't know, a check mark, for example. So one here, and one here. Looking at these points alone, I will see that they have a very large variation, and I will estimate that as the Gaussian function that has its peak somewhere in between, because I'm calculating the mean value, so it's somewhere somewhere in here, and it's very this function has a very large variation. So it should look something like, I don't know, something like this. And as you see, all these spiky Gaussians, they will some sort of, I don't know, like a shots. They go through this Gaussian, and they prescribe much more probability to be a class of, I don't know, crosses, squares, or circles in the vicinity of their maximum. but they are very sharp, so they quickly go to 0, and then this large goes and overpowers them and prescribes larger probability to all that points that are far from their maximum. So that's why we are having the picture that we have. And that's why we see that all these points are prescribed to class D, despite the fact that we have no point of class D in this region. Okay, one more demo to show you. That's about so-called ROC and EUC. We have a binary classifier that we are using to classify two classes. In the previous lectures, I told you that it may be quite troublesome even to say which classifier is better, even if we are just working with a binary classifier. So that may be already a problem. And here is one of the example how we are trying to overcome that problem. Of course, we can't fully resolve that, but at least we can try. And moreover, it's one of the ways of tuning that classifier. So here's an example of that. I can I can add some points of two classes, blue and red. Once again, you see that I have all these estimates for their distributions. I'm putting red points on the top here, but it doesn't basically mean anything in the sense that I'm working with one feature, that's their x coordinate, and this position only let's say underlines the fact that I'm trying to calculate the probability to be class red, and class blue I'm just treating like 1 minus that probability. So this curve is estimated red probability is the probability to be class red. And I can, with this sort of estimation, I can treat it like the whole family of the models, because I can set a threshold when do I treat points like being class red, and when do I treat them as being class blue. So now I'm changing that threshold, and you see that that results in the table, the number of false positives, false negatives, and so on and so forth, they are changing. Depending on how they change, I can create a so-called ROC curve. Here you see false positive rate and true positive rate on x and y axis, and here is the curve that depends basically on the threshold that I am taking. So I'm changing threshold, I'm getting different numbers in here. And basing on this curve, you can try to estimate which model you like more. Of course, it's once again it is complicated, because if you have models that have the same let's say a true positive rate, of course you will choose the model with the smallest false positive rate. But if you have picture like this, you understand that there is some sort of trade-off between false and true positives, and you can't get everything in one model, and you should choose the model which you like the most, basing on this curve and basing on the fact how crucial is it to have less false positives, or how is it crucial to have more true positives. So always remember about so-called business metrics and what do you want to get from your model at the end of the day. So you can play with this demo and once again get some insights into that bias and into that choosing models. That's just small recall about precision and recall. So hopefully you remember that formulae, and these are the parameters that we often use to estimate our models. Be careful with imbalanced data sets. Once again, if your data set is imbalanced, you can get into some sort of trouble that intermingles with your prior, and you should take that into account. Few methods to calculate everything, so it's like sort of area under the curve that tells you that is integral of ROC curve or mean procedure, or you can calculate f-score, so that depends. So these are different methods that you can try to use to estimate how good is your classifier. But anyway, despite having all these methods, at the end of the day, everything always boils down to the fact that you want to have some business metrics, and you need to take that into account. Okay, and now the last part, text classification. So very often naive Bayes is used to classify texts. I want just to briefly show you some sort of ideas behind this. So for example, if you are classifying some texts, what can we do? We can look at the words that are used in that text, like we did with, for example, with letters, and we can try to classify that text basing on how often do we see some words in there. We may have different models of that, and there is maybe the simplest model is so-called bag of words. And it boils down to picture like this. So I have, let's say, class physics and class literature. I know that different words are used with different frequency when I'm writing some sort of poem or when I'm writing an article in physics, so there will be different choice of words and different frequencies of that word. I can treat a document like some sort of generated sample that I get by randomly choosing some words from the bag. And here is the question in sense of Bayes theorem. So I have few such bags that correspond to my classes, and I have a document, and I say, okay, this document, this collection of words, it was drawn from one of the bags. So one of the bags was chosen. I have drawn some random words from there, and I have gotten this sort of document. Now I need to perform the reverse engineering. So having the document, I should guess what is the probability that these words were drawn from the bag physics, and what is the probability that these words were drawn from the bag literature. So here is such an example. So let me do one more, just drawing. So here I keep words typical, for example, to physics. Here I keep words typical, I don't know, for biology. Maybe some different stuff, and so on and so forth. So here is my document. I suppose, so my model is that it was generated by first choosing one of these bags. So for example, I chose, I will write an article in physics. And then I was drawing, here are some words living in here. I was randomly drawing these words and putting them into this sort of document. That's what happened. Now, this information is lost. And I only have this document with the words. And comparing their frequencies to whatever I have in here, and in here, I should somehow draw the conclusion which one of the bags I was using when generating this document. That absolutely goes in line with the problem I have posed with jars and balls. When I was taking balls from some jar in a dark room, not knowing which jar I am taking them from, then I went somewhere outside, I checked the color of the ball, and I was trying to predict what is the probability I have drawn that from that jar or from that jar. Absolutely the same thing. These are jars with words, You have drawn them, you have a document, now you are trying to predict where did you get them from. And in this case, we often use so-called multinomial naive bias. Once again, I'm not getting into all these formulae. Hopefully you know what is the multinomial distribution. Here you have expressions for all that probabilities. So we are, once again, we are basing on some model. This model is multinomial distribution, so it's some sort of random drawing of words from bags where their probabilities are fixed. And here is an example of calculating all of that. So I'm not showing you the whole code, but you see that we use that information to get some sort of text classified. To do the work done, you will most probably use so-called vectorizer that will transform your text into that features, and you can use different vectorizers like count vectorizer that you use for that multinomial bias, or you can use some different vectorizers, so on. One of the most interesting is so-called TF-IDF, so term frequency inverse document frequency, calculated a bit complicated with this formulae. So I'm not getting into it, but just know that it exists. Okay. I guess that's basically everything I wanted to tell you. So at this point, we have considered the naive bias, and we have performed some sort of text classification with that. And hopefully now you know how to use this very simple but quite interesting classifier.